Now that you've learned how to plot some points, we're going to continue on with our goal of how to graph some lines. So we're going to get there, and we're going to get there kind of slowly because I want to get in your head what a linear equation in two variables actually means. So we're going to get there by studying what a linear equation in two variables really looks like, how to identify them, and then how to use what you learned last time, these plotting points, to make your first ever line. And then we're going to learn a lot about it. So this lesson isn't one that's it is going to be easy at first, but it's not one that you want to gloss over. Because what I'm going to start to do and how I like to teach you, I like to teach you kind of a few videos or lessons in advance. So what you're going to learn at the very end of this lesson and throughout this lesson, you're going to be using for the rest of your time, like forever, in graphing lines. So let's learn about what a linear equation in two variables is, how to identify them, and how they work. Firstly, any equation that makes a diagonal line on a graph is going to have exactly two variables. It's going to be an equation. It's going to have exactly two variables, and those variables are going to be raised to the first power. This should sound familiar because we talked about linear equations in one variable already and how to solve them. So now we're saying, what about if they have two variables? What's that going to make? And here's what we're learning. Linear equations are equations that have two variables, two different variables. Each one's raised to the first power still, and they are going to make diagonal lines when we graph them. So that's kind of cool. Right now, I want you to look at these equations on the board, or these expressions and equations on the board. Let's identify which ones are linear, which ones aren't. Which ones are going to make diagonal lines when we graph them, and which ones won't. Check out the first one. Firstly, ask yourself in your head, is it an equation? It should be like, bam, you know the answer. Of course it is. It's got an equal sign. How many variables do you see? Are those variables raised to the first power? Remember, with our variables, if you see a variable, it has a power. If you don't see any power up there, it's a power 1. Right here, that's a linear equation with two variables. This is an equation. It's got an x variable, it's got a y variable, and they're raised to the first power. This is going to make a diagonal line when we graph it. What's interesting about linear equations in two variables is literally it's a relationship that shows you how one variable is related to another variable. It says take a number, do some junk to it, and it's going to give you another number. That right there, oh wait a minute, that sounds pretty familiar. Because if you take one number and you put it in there and you get a different number, another number out, that's a relationship amongst two numbers. You could pair those numbers up in some sort of an order and get an ordered pair. Something you can plot. This is exactly what we were talking about in the last video. A relationship among two variables, a relationship among two numbers that we can plot on a graph. That is exactly what linear equations in two variables gives you. It gives you a relationship amongst two numbers, two variables that give you numbers that you can plot and make diagonal lines out of. That's all this stuff really is. We're going to look at this one later, just a bit. Now let's identify the rest of them. Is this also a linear equation? Be careful here. Is it a linear equation? I know you want to say yes because you see two variables. And yeah, those variables are raised to the first power. But it fails in one way. How does this fail to be a linear equation? It's not an equation. This will not make a line when you graph it because there's no way for us to say whether or not we get a true statement by plugging in numbers. We can't get that. You see, when we talk about points being on a line, we've got to take those coordinates that are from the points that are on a line. They have to go into our linear equation and make a true statement, something that we can verify to be true. Those points will be on the line. You can't do that with that. Now, if we do this, equal to, say, 10, no problem. That right there is a linear equation. It's got an equal sign, equation. It's got two variables, x and y. They're in a relationship. That's awesome. Probably a good relationship. It's going on an ups. Well, that's actually, yeah, going so. Oh, wait, no, that's a negative relationship. It's going downward. It's going to negative slope. We'll talk about slope a little bit later. We're going to learn how to graph all this stuff pretty quickly. But right now, all I need you to understand is that these are both linear equations. They're equations. They have two variables. They're both raised to the first power. If you don't have an equal sign, this is no longer a linear equation because it's not even an equation. Look at the next one. Is it an equation? Does it have two variables? Does it have more than two variables? As soon as you say yes, that's no longer a linear equation in two variables. That right there would be a three-dimensional object. When we start talking about x, y's, and z's, we start getting more complicated ideas. For us, it's beyond the scope of the class right now. We'd be talking about planes. We'd be talking about lines in three space. We're not there yet. This right here would not make a diagonal line on the plane. You start talking about more than two variables. You start talking about something that's beyond linear equations and two variables for us, not on a plane anymore. How about that? Is that a linear equation? Yes. You got an equation, you have two variables. Now, I don't really care that those variables aren't x and y. You can have any two variables, that's fine. You're not restricted to having all x's and all y's all the time. You can have an x and a z axis, that's okay. This would still be a linear equation right here in two variables. So yes, automatically, no, it's not an equation. No, it's got three variables. Yes, that's a linear equation. How about the last one? Is that a linear equation? Well, does it fit? Is this going to make a diagonal line when you graph it? Well, if it has an equal sign, sure. If it has two variables, what are your variables here? Yeah, I got b and I got t, and they're both raised to the first power. That's going to make a line on a graph. In fact, we're going to do it in just a minute. This, you can't even make a graph out of it. There's nothing to tell whether the points would be satisfy that equation, be true or not. It's not an equation. Here, this would make a line on a graph. Yes, that's a linear equation. Put this back. No, that's not a line on a plane. This, yes, even though you have different variables b and t, that's okay. This is a linear equation. This would make a diagonal line when we're relating a t variable to a b variable, a t-axis and a b-axis. Now, which one's horizontal and vertical? We'd have to just kind of choose. There's no really way to tell on this problem. You choose t horizontally or t vertically. There's nothing really given to us here. But it is going to make a diagonal line on a t combined with b axis. That's going to happen. What if I did this? As soon as you start adding exponents to it, or I should say implementing or introducing exponents that aren't ones onto these linear equations, they no longer become linear. They start becoming other types of curves, like parabolas, like hyperbolas, things like that. So they're no longer lines. Therefore, they wouldn't be a linear equation. They're not going to make a diagonal line on a graph. So hopefully at this point you understand what that means. It's really just all right here, but I need you to be able to identify it really easily and quickly what's going to make a diagonal line and what isn't. If you have an equal sign and you have two variables, each of them raised to the first power, yes, yes, no, no, yes. Those will make diagonal lines when you graph them on a rectangular coordinate system, xy plane, Cartesian plane, any one of those things. Now, in order to get there, in order to actually kind of get some points to graph, because right now we don't know how to graph lines, we don't know how to look at that theoretically. Maybe you've had the class before, I don't know. You can look at that and graph. That's awesome. We're going to get there. We're going to get there fairly quickly. In fact, by the end of this lesson, I'm going to start teaching you ahead of where we're at, just so you get the feel for how this stuff interplays. We're going to start graphing that, but if you have no idea how to graph y equals 3x plus 2, we're going to need some points. You see, you do know how to plot points. You know what an ordered pair is. You know that what variable comes first? What variable comes second? When you have this ordering, we always know that our first number in that ordered pair is going to be your horizontal axis number, typically x. And your second number is going to be your vertical axis number, typically y. We know how that interplays. That was the last video. What we don't know is how to graph a line yet. That's what we're going to get to. I want to be real clear here. When we're going to graph lines, and we're going to learn a technique to graph lines in the next few videos, it's going to be a means to an end. By the end of these videos on graphing lines, I do not want you graphing lines by plugging numbers in. I swear that's weak sauce, all right? It works, but it's inefficient. Effective does not mean the same thing as efficient. What I want you to be able to do is look at that and graph it in about 5 seconds. I'm not even joking, like 5 seconds. You should be able to look at that line. By the end of these videos on graphing lines, you'll be able to graph in about 5 seconds. That's what I'm going to start teaching you here in just a moment. Right now, we're not there. Right now, we need to get a feel for how this interplays with the line we're about to create. In order to get there, we do know one thing, two things really. We know what points are, ordered pairs. We know how to plot them, that's great. And we know how to check for solutions. In fact, we know how to check for solutions by just plugging a number into an equation and seeing if it makes a true statement. That's really all we know how to do. Let's try that. Let's take some ordered pairs I'm going to come up with, not at random, but I'm going to see if we can get here. Let's take an ordered pair like 1, 5. Okay, real quick, in your head right now, think it to me. What's the x coordinate of that point? I'm thinking x's and y's. I get x-axis, y-axis, so I'm thinking x's and y's here. What's the x coordinate? What's the x value of that point? You should know it right now. What's the y value of that point? In fact, if it takes you labeling it in alphabetical order as x, y to identify it, that's fine. Here's the main goal. Can you tell me whether this point is a solution to this line? Yes, it's got two variables. It's an equation. Each variable is raised to the first power. It's going to make a line. Is this point on that line? The answer to that question is whether or not it's a solution. If you plug in the coordinates to the correct variables and you get a true math statement, it's saying that point is on that line. That's cool. That's the whole nature of using points to graph lines, using a table to graph lines, and we're going to do that later. Right now, I just need to know if it's a solution. If it is, it's on the line. If it's not on the line. In order for a point to be on a line, the coordinates of that point must satisfy the linear equation. That's a pretty big note. You might want to write that down and study that a little bit later. You got to have that down. So let's check it out. Well, it's kind of convenient, right? I mean, we got an x, we got a y, we got an x and a y. Let's take the numbers, let's plug them in, just like you'd be checking any other solution for an equation. Let's see if it works. So draw whatever you want, colon, arrow, whatever. If your x value is 1 and your y value is 5, all you really need to know how to do is take the correct numbers and put them in the correct places. Your y value is 5 here for this ordered pair, for this point. Make sure that your y value in your equation, in your linear equation, becomes 5. So where am I getting that from? Why am I getting 5 equals? Well, because I know that my y value, in order for this to work, in order for this point to be on this line, the y value here must take the place of that y. So we'd have to check this. We'd have to plug this in and check this, substitute in and check this. On the right-hand side, my 3 doesn't change. My x does change. My x takes the value of 1. I'm taking for granted that you know about substitution, that you know about evaluating equations with certain values. We've done that before. That's also in the pre-algebra videos. So if you're like, what are you doing? All I'm doing is replacing the variables with the numbers that this point says they have to be in order to satisfy the linear equation and be on the line. That's what I'm doing. Let's see if it makes a true statement or not. 5 came from this 5. The y became 5. The x became 1 to check whether the point's on the line. This 5 is done. On the right-hand side, you do some simple math. You do some order operations. You go, hey, 3 times 1 is 3 plus 2 is 5. Oh my gosh, yes. That's a true math statement. The two sides are equal. That's fantastic. What that says is that this point, when I plug it into my linear equation, create a true math statement, says that this point is on that line. All linear equations with two variables make lines. That's cool. It says that that's a point on that line. If you get a solution, which this is telling you it's a point on that line. So I'm going to erase our work here, and I'm going to put solution. Maybe I won't erase it. I'll just put solution. Says that point's on the line. Let's try another one. Let's try -2, -4. Hopefully you've practiced the idea of ordered pairs. You know what the x value is, like right now you know what that is. You know what the y coordinate is, like right now you got it. Take those values, plug it into the equation. The same equation. You see, we're going to try out these points as a good fit, whether they're on the line or whether they're not. The ones on the line, we're about to graph it. The ones not on the line, well, we're not going to graph it because that would not satisfy the linear equation. Therefore, if we're trying to graph a line, do you really want to show points? If you're trying to graph a line, do you want to show points that aren't on the line? Well, no, those are useless points. So we're basically just guessing and checking our way through finding points to a line. Are there better ways? Yeah, a lot better ways. We're going to discover them later. Just get a feel for what's going on here. What's your x value? What's your y value? Take some time to plug it in right now. If your x value is -2 and your y value is -4, then when you plug that in, when you substitute it or evaluate this equation for those values, we're either going to get a true statement or we're not. If we get a true statement, it says we have a solution, it says that point's on the line. If we get a false statement, it says that point's not on the line, we don't get a solution. By the way, you're going to notice something. You almost can't overuse parentheses when you are evaluating things. What I mean by that is if you're ever going to plug a number in, man, put it in freaking parentheses. It's going to maintain your operation. It's going to maintain multiplication. All it does is house the negative number so you don't accidentally think it's subtracting. It's really good to evaluate by using parentheses where your variable is. So replace your variable with parentheses, and you really can't mess up order operations that way. It's kind of nice. I guess you can, but it makes it hard to do. Almost have to try. So let's see. On the left-hand side, we'd still have -4. We're just doing order operations. We're not solving for anything. We're just evaluating to see if we have a true statement. On the right-hand side, calculator, use your head. Make sure you do order operations though. 6 times -2, well, that's -6. -6 plus 2 is -4. Whoa. We get another true statement. That's true. That says that this point is also a solution. By being a solution, it's another point on the line. Now, how about this question for you guys who are thinking out there? Could you stop? Could you stop right now, put these points on that graph, and connect them? How many points do you really need to make a line? Well, you need more than one. So if I just put 1 point, I could draw a whole bunch of lines right there, like a ninja. You could do a whole lot of stuff, a whole lot of lines through that point. But as soon as you draw 2 points, plot 2 points, there's only one unique line on that plane that travels through those 2 points. That's it. You could literally stop right now, plot these 2 points, and make a line through them. And inherently, by making that line, you get all the points on the line. It's kind of cool. Now, that kind of is not what we're doing here, but you could do that. Let's discover what happens when we get a non-solution, how that would manifest itself. So let's take -2, -3. Same x value, different y value. If you have the same x value and a different y value, that would be on a vertical line, not a diagonal line. I'll tell you something right here that you're going to unpack later. Vertical lines do not have 2 variables. Horizontal lines do not have 2 variables. In order to get a diagonal line, you have to have 2 variables, a way to represent a horizontal motion and a vertical motion. If you only have 1 variable, you're kind of limiting yourself to either only vertical or only horizontal. So if you have two variables, I guarantee you are going to have a diagonal line. Let's check this. I know you know your x. Your x is -2. Your y is -3. Let's plug it in. Your y value would take -3. Your x value would take -2. Yeah, use parentheses. Keep that negative housed in there. It maintains operations. That's awesome. -3 looks pretty darn good. On the right-hand side, we have 3 times -2. Well, okay, that's, oh man, it's the same as this. It's going to be -4. Is that a true statement? Well, no. What that tells you is that this point created a false statement. This point is not a solution. Solutions create true math statements. That's a false statement. So basically, it's telling you exactly this. It is false that this point is on that line. That's what it's telling you. It's false that this point satisfies that equation. Since that equation is a line, it's false that this point's on the line, not a solution. Tell you what, I would like to give you a few more, just 3 more. I would recommend that you try them on your own. I'm going to give you the points 5, 19. I'm going to give you the points 0, 2, an important point. Oh my gosh, I can't stress enough how important this point's going to be for us. And then just to mess with you, I'm going to give you this point. You know how to do it, right? I had to give you fractions just to show you that they're actually relevant. A lot of times we get to graphing and we go, finally, I don't have to deal with fractions. But most of the time you don't. I'm going to teach you ways to not have to deal with fractions. But they do exist, and they are on our lines. Lines are continuous beings. They have, if you have a line, they have points everywhere on that line. They're not just like 2 points. They're an infinite number of points stretching forever. Just like on an interval. Remember the intervals went from negative infinity to like 5 or whatever? All the numbers between there are solutions to whatever inequality you had. Not just like -1, -2, -3, -4, but -1.5, -1.563. All those values. Fractions happen on graphs as well. I'll show you how to work with it. So as I've been rambling, hopefully you've been working. Here, this one. Your x is 5, your y is 19. You make sure that your x value goes where your x is, your y value goes where your y is. So we would have 19 is supposed to equal, we're kind of checking here. You're going to notice I still put that 5 in parentheses. There's nothing wrong with that. Even though you don't really need the parentheses here, notice how it maintains the operation of multiplication and it houses that number. If that number had been negative, that'd be a really good thing. Parentheses rarely screw you up. I can't think of a time when you would evaluate and not be able to use parentheses to contain that number. It still maintains operations. It's a really good thing. Try that. So here on the left-hand side, we have 19. On the right-hand side, we have 17. And you tell me, is that a solution? Is that not a solution? You go, well, that's obviously not true. It's a false statement. It's false that this point is on that line. Are you getting the connection? Are you getting the connection that all we're trying to do here is make the connection in your head that that's going to make a line. These are points. By being solutions, they're saying these are points on that line. But being non-solutions, saying it's not a point on that line. Not a solution. The next one. I'm going to spend some time once we finally plot this and talk about that particular point and how it works. You see, it's a really important point. If you look at that point, what's your x-coordinate? Do you remember talking last section, or last video, I guess, how, 2 videos ago, how when you have a 0 for the x, or conversely, if you're on the y-axis, you have a 0 for the x-coordinate. That's a big deal. If I'm somewhere on this y-axis, I do not have a positive x, otherwise it'd be to the right. I do not have a negative x, otherwise it'd be to the left. I am somewhere on this y-axis. That's a big deal. If we can find that point every time, the point where a diagonal line crosses the y-axis, and you will have one if it's diagonal, it has to. If we can find that point every time, by considering an x value that's 0, like that one, if I say, hey, just find the point on here that has an x value of 0, you're going to find the point on the y-axis. We call the y-intercept. We're going to figure out how to do that a little bit later. If you can find that, that's going to help us with our graphing. Let's plug that in. Our x-coordinate is 0. Plug it in. Our y-coordinate is 2. Plug it in. Our y became 2, our x became 0. Notice you're still multiplying. 3 times 0 is 0. 0 plus 2 is 2. Yeah, that's a solution. That tells us this. That tells us that this point is on that line. This point of, could you plot it right now? Could you do it? This point of 0, 2, x-coordinate of 0, y-coordinate of 2, that combination of ideas, that interplay, that relationship is right there. It tells you this. It tells you that your diagonal line is going to cross the y-axis. It's called y-intercept at the point 0, 2. That's where it's going to be. It's kind of cool. Now we're going to talk about the relationship of that equation in just a moment. The last one. Man, fractions are nasty. If you ever pick points yourself, and we're going to do it in the next video, try, and you have fractions. Try to pick values that eliminate your fractions. For instance, if you had a fraction of 1/2, you'd want to be picking stuff like 2, 4, 6, Things that you can multiply by 1/2 and eliminate the fraction. I'm big on that. If you got equations, you can eliminate fractions. It's kind of cool. With this, I haven't given you too bad of a fraction. Your x value is your fraction. Your x value is 1/3. Your y value is the 3. So if we plug this in, yeah, our y value becomes 3. This 3 stays the same. Our x value becomes 1/3. And then we add 2. What's 3 times 1/3? Calculator, or you think, well, cut a third into 3, cut 3 into 3 equal parts. Divide it into 3 parts. That's going to be 1. 3 times 1/3 is 1. 1 plus 2 is 3. That point is on, even though it's got fractions in it, that point is on that line. That's a solution. Now here's what I want you to do. Pause it or work through it. I want you to cross out the stuff that's not solutions, or just ignore the stuff that's not solutions, and plot the 4 points that are solutions. The 4 points that tell you, true, this point's on the line. True, this point's on the line. Not true, don't do that one. Not true, don't do that one. True, this point's on the line. True, this point's on the line. And oh man, you better get something that's linear out of this, something that's a diagonal line. Let's check it out. So try it on your own. I really need you to be able to plot at this point. If we plot this 1, 5, I'm going to go quickly because we should be pretty decent at plotting points. 1, 5 says x value of 1, y value of 5. We have no whole number, capital letters as labels, so we don't really need to label the points themselves. We're just going to know that that point is a solution. It was a true statement. It's going to be on the line. -2, -4. -2, -4 is right here. -2 on the x, -4 on the y. We're in quadrant 3 here. Remember that? Quadrant 3? I don't want to do that one. Why would I plot something if I'm trying to graph a line that's not on the line? That's crazy. That would lead to squigglies everywhere. We don't want that. 519, again, not on the line. I don't even worry about it. Thank goodness, because it's really big. 0, 2, yes. 0, 2, 0 for x, it's right there, combined with the idea of having a value of 2 for the y. Notice how I don't have to go in any sort of order at all. I could have plotted these in any sort of order I wanted, as long as I get all of them, and as long as I haven't made a mistake in checking my numbers. All these points are going to be on the line. Interesting. Last one, 1/3, 3. Do you remember how to plot fractions? Do you remember that this is positive? It's got to be to the right of y. This is positive. It's got to be above x. It's got to be somewhere in quadrant 1. It's going to be. It's just not on one of these whole numbers or integers that we're used to. 1/3, 3. It's about there. About 1/3, combined with the idea of having a height of 3. Now, I hope you did it on your own. I hope you looked at it. Does that look like it's a line to you? I hope so if you get your graph right. It has to be. All of these things make diagonal lines. They all have to. So if you're finding solutions, if you plug in 2 numbers, this ordered pair, and you're getting something that's a true math statement, you have a solution to it. It's telling you it's true that that point is on a line. That's kind of cool. That's how we graph using points. So we just discovered 4 points that are solutions, 4 points that are on that line. When we plot them, man, it's a straight line. You can take out, hopefully I've done mine right. Draw a line through them. I'm going to cheat and make my points bigger, because my scale's not perfect. That's why that happens if you're not using graph paper like me. Your scale's not perfect. One other thing. There's not just 4 points on this line. When you draw a line in math, you're representing that this is a continuous stringing out of points that are all together. All the points would be satisfying this equation that are on that line. This goes forever. Forever and ever. That right there, ladies and gentlemen, is what a linear equation in 2 variables creates. It creates a diagonal line that you're graphing. We can do it by checking some points and figuring out whether they're true or false. Is this efficient? No. I created these points myself. Would you know how to create points that work automatically? No, that's kind of hard to do. Is there a different way? Yeah, that's what for the next lots of videos, we discover easier ways to do this. Now I'm going to erase all this junk because I want you to notice some stuff here. All but this one, I'm going to erase all this stuff. I want you to notice something. This is the big deal. Here's the takeaway from this. This is going to lead you to your next few videos. I don't really care about this one. It was important. Got us to do our line. I don't really care about this one. I care about this one. Okay, focus here. This is a big deal. This is what I need to get you to really, really get. I need you to understand that there are some very interesting and extremely useful connections between this equation, how it looks, and what this line does, how this line is, and that they relate. Here's the biggest deal. Right now, could you take your pencil and could you put it on where the line, the diagonal line, crosses the y-axis, not the x. I don't care about that right now. I care about where the line crosses the y-axis. Can you please do that? So right now, I'm not talking here. I don't care about that. I'm talking about put your finger, put your pencil, put something on where this thing touches the y-axis. And you should have your pencil right there. Now, that point was this, wasn't it? That's 0, 2. That point, and it's not a big surprise, that point has a y value of 2, but it has an x value of 0. Right here, that's an x value of 0 for everything on that line. For everything on the y-axis, it has an x value of 0. That right there has a point, well, x coordinate of 0, y coordinate of 2. Here's the takeaway. I want you to look here. What's the y value? What's the y value of that point? Do you see a 2 somewhere in this equation? Of course you do. I mean, it's kind of rhetorical. Yeah, it's right there. This will always happen. I promise you, always. This is a huge deal. If I can get you to learn this, the next few videos, well, several videos from now, are going to be really easy for you. And right now I'm trying to teach you ahead of where we're at. Just so when we get there, it's not going to seem like, it's going to be like, oh, that's what you were talking about. This is what I'm talking about. Check it out. That number, if, big if you have your y isolated, do you see it's isolated? No addition, subtraction, multiplication, division, but it's all by itself. If you have your y equal to some term in x plus a constant, this is called slope-intercept form. And we will get there. I promise I'm going to teach you all about it. I don't ever skip. I don't ever go and not explain things. I will explain all this to you. But if you have this in this form, that constant at the very end, after your x, y is isolated on one side, x is on the other side, and you have a number that's being added or subtracted, that number will always, always tell you your y-intercept, no matter what. So it's not a coincidence that this is a 2 and you go through 0, 2. Not a coincidence. In fact, I can prove it. If you were to plug in x equals 0, plug in x equals 0, 3 times 0 is 0, you would get a y value of 2. That's telling you that if you make your x 0, you're going to be on the y-axis. You have to be. That's the only place where x's are 0. You're going to be somewhere here. If you plug in x equals 0, it's going to tell you where you cross the y-axis. That's awesome. So let's pretend for a second. Let's say this wasn't 2. Let's say this was 7. Could you tell me where your line has to cross the y-axis without doing any math at all? You're isolated. You got a y on one side, got an x on the other side. You're adding 7. That's a plus 7. That's a positive 7. I guarantee you, your y-intercept slope-intercept form. The intercept stands for the y-intercept. You will cross this y-axis at 7 up here somewhere. It has to happen. What if this were -1? If it were -1? Well, plug in 0 for your x. You have 3 times 0 is 0. -1 is -1. You will be crossing the y-axis at -1. Do you see how this can shortcut a lot of your work? You don't have to guess at points. You don't have to plug in anything. All you have to do is have the equation in the right form, and it will tell you where this line crosses the y-axis. That's a big deal. Why? Why is it a big deal? Well, how many points do you really need? Did you need all 4 points to graph this line? Not really. Could have done with 2. What if you knew where the graph crossed the y-axis? That'd be 1 point already. You'd only need 1 more. that number will give it to you every time. So in this case, I know this line is different than this line. This line would cross the y-axis right there. It would have to. Because if you have your x being 0, the only thing that's left is that constant. How about a tough one? I hope I'm getting through to you. Hope I'm getting through to you on how these things interplay. This is the line that we graphed. That 2 is that 2. This line is different than this line. Would look very similar, but would cross here at 4. This 4 is that 4. This line would be very similar to this line, look almost the same, but it would cross right there. This -1 is that -1. Why is it negative? If you put in 0 for x, 3 times 0 is 0. 0 minus 1 is -1. Y would be -1. That's what I'm talking about. That's the interplay. It's pretty cool. That is going to end up saving you a whole lot of time. When we get to graph by slope intercept, I'm just teaching you now so that later my job is easier. And your job is easier. Let me put it back. Last one, probably the big one. They're both big. I mentioned to you that if you could find 2 points, you could graph a line. Your y-intercept right here will always give you 1 point. If you could find some way to get another point, that'd be awesome. You would have to plug in no values at all and graph a line in about 5 seconds. I need you to notice how this 3 affects this line. So here's what I want you to do. Can you look at that 3? Can you make a number into a fraction? How do you make a number into a fraction? I think you'll probably all know the answer to that. If I wanted to change any number into a fraction, I can always put it over 1. I've done it before. So notice something. This only works. Okay, all this stuff is predicated on the fact. It's based on the fact. It needs to be based on the fact that you have y by itself. That's a huge deal. But check this out. This is awesome. If I look at the number in front of x, we call it the coefficient. If I make it into a fraction, check this stuff out. This is phenomenal. Not phenomenal, how this stuff works, but it's pretty cool. That 3 over that 1 tells you how you get from point to point to point to point. If you've had the class before, it might not be a big surprise, but it's a huge deal to understand. I want to get you past plugging in numbers to find points to graph. That's so slow. It's effective but not efficient. We're all about efficiency, doing stuff well, but quickly, but well. Check this out. This is awesome. This will always tell you, this number is called the slope. It'll tell you how to get from point to point to point to point to point. Check this out. Start here if you want to. It will tell you the top number tells you how much you go up. The bottom number tells you how much you go to the right. Never left, always right. So this says, I want to go up 3 places and over to the right 1 place. Oh, sorry, I started wrong. I started here. I want to be at -2. Go up 3 places. 1, 2, 3, and over 1 place to the right. Oh, that's another point on the line. It has to be. That's the way these linear equations work. I don't even know it, but I guarantee you, if you plug in -1, comma -1, -1 for x and -1 for y, it's going to be a solution. Check it out. Plug in -1 for x, you get -3 plus 2, that's -1. Plug in -1 for y, oh, there you go. How about that? It's a solution. It has to be there. Do it again. Go up 3, 1, 2, 3, and over to the right 1. Remember, it's rectangular, so it's like a knight move in chess. Never mind, too many jokes. You're like a knight move, so you're making L's. It's rectangular. You're following the edge of a rectangle here. Up 3, 1, 2, 3 over 1. That's another point. Oh my gosh, does it still work? Up 3, 1, 2, 3 over 1. Yes, you can find any point that you want. Up 3 over 1, up 3 over 1, up 3 over 1. That's cool. Wait a minute. That's how you can find another point. So wait a minute. How many points do we need to graph a line? Can you find 1 here? Yeah. Can you find 1 by using this slope? Yes. This is how slope intercept is used. I'm going to quiz you a little bit here. This is above and beyond, okay? All you really need to know for this section is that you can plug in values and from the points and see whether there's solutions or not. Solutions mean points in the line, non-solutions don't. But I want you to learn more. I want you to be better than just understanding that. These numbers interplay here. This number, this constant, is your y-intercept. This number in front of your x, your coefficient, that is your slope. It's how you get from point to point. If I did a... That's pretty advanced for some people. It'd still tell you something. In fact, if you want to graph it right now, graph it right now. That number, -4, check out the form. Your y value is first. It's isolated. On the right-hand side, you have your x term and then a constant. That value, that -4, if you plugged in 0 for x, you would get 0 minus 4, that's -4. You would find your y-intercept. This number, that constant is where your line, verify, linear equation. Two variables, each have one as their exponent. This has to cross at -4. If I change it to a plus, I'm going to keep it there because it'll be a better graph for us. This would have to cross at +4. Have to cross there. Your slope tells you what to do next. This tells you, remember that one time I told you always associate your negative with your numerator? So that a couple times, move it up to the top. So -2/3 becomes -2/3. This will tell you how to get to your next point. You only need 2 points. This gives you one of them. Your slope tells you how to relate to your next one. This tells you go, what would you do if I said it's -2? I say the top number tells you to go up or down. -2, would you go up? Would you go down? So from here, go down 2. The bottom number tells you how much you go to the right. Never left, ever. Down 2 and to the right 3. That's your line. If you connect those 2 points and make it go forever, you just graph that line, and when you get used to it, you can do it in about 5 seconds. I call it 5-second graphing. It's also called Slopeintercept. It's pretty fast. Here's the whole takeaway from this lesson. I need you to know that linear equations are these equations that have 2 variables, each raised to the first power. I need you to know they make diagonal lines. I need you to know that you can always test an ordered pair. Plug it in. If it's true, a true statement, it's on the line. The point's on the line. If it's not, the point's not on the line. By connecting those points with a line, we get a picture of what this linear equation represents, a diagonal line on a plane. There's some interplay with the numbers that you're using here. If you get it now, it's going to save you time later. If not, I promise you I'm going to get to it later. But these numbers are relevant to the picture that you're getting. Hopefully I've kind of just broken through the surface a little bit. I don't want to fully explain it yet because I'm going to have a little bit more background before we get there. I just want to make sure that you're exposed to it here. If I've done that, awesome. Watch it again if I haven't. Try to see how I'm going from here to here. What that is. If you get it, that's awesome. You're going to do great at this. And I'll see you for the next video when we start graphing lines with some points, and I'm going to start exploring this idea more and more. By the end of the next video, you're going to start seeing these numbers pop up in our lines. Hope it made sense. I'll see you next time.